Hey guys, so this lesson is going to be going over arcs and chords on circles. So we know a lot about circles from an earlier unit when we did area and circumference. We worked with segments, sectors, arc length, arc measure. And now we're going to look at arcs and chords and radii. So first of all, what's a chord? A chord is any line segment that connects from one end being on the circumference of a circle to the other end also being on the circumference of that same circle. So this line right here is an example of a chord, and so is the diameter. The diameter just happens to be the longest chord in a circle as it passes through the center. Now we have an example here, number 1. So I'm going to work on the odds with you, and you're going to do the evens for homework. So we have an example here where this little line segment going from the center to the edge of the circle or the circumference has a length of 7.1. And now this piece right here going from that right angle to this point right here has a length of 6. And you're being asked, how long is this piece going from right there to right there? Well, if this piece right over here, the radius is 7.1, what else do we know? We also know that this piece, which is also the radius, has a length of 7.1. Now, if we add another segment into this picture right here, we could actually draw in one more radius. This piece will also have a length of 7.1, since the radius of a circle is the same throughout. If I have this segment here being a shared side between these two triangles, we can basically use the reflexive property to sort of give this little line segment to this triangle and to this triangle as well. Then we'll have two triangles. If we have that it's perpendicular right over here, right angle, it's also perpendicular right there. Since this is a right triangle and another right triangle, we have congruent hypotenuse. Hypotenuses. The hypotenuse is congruent from one triangle to the other, and one of the legs is also congruent. Well, that means that these two triangles are congruent based on the hypotenuse leg theorem. Therefore, we can state that x is equal to 6. And that's the end of example 1. What about example 2? 31.8, being labeled right here at this point, is telling me that this entire distance is 31.8, the diameter, from here until here. If I divide 31.8 in half, I will get the length of the radius, because the radius is half of the diameter. Half of 30 is 15, half of 1.8 is 0.9. That means that the radius is going to be 15.9 throughout. This line right over here is also 15.9. If this piece is 15.9, and I also happen to know that the piece from right here to right here is 7, how can I figure out the length of x? 7 plus x must equal 15.9. Subtract 7 from both sides, and we find that x is equal to 8.9. Now let's look at number 5. 25.2 again is written right by the center point, so that tells me that's the length of the entire diameter. So that would tell me that the radius is half of that. What's half of 25.2? Half of 20 is 10, and half of 5.2 is 2.6. So the radius is 12.6. That's the radius. That's the radius. And this whole entire line right here is also the radius. Now I start kind of analyzing and coming up with information before I even really look at where x is, if you notice. Now, if that whole segment is 12.6, what can I do to figure out the length of x? Well, one thing we can do is we can state that 12.6 is equal to x plus 4.5. Subtract 4.5 from both sides, and we'll have that x is equal to 8.1. Is there another way we could have done this problem? How about using this right triangle over here? Could we have used the Pythagorean theorem? Well, right here we have 9.7 as this piece right over here, this segment. And if this is also 12.6, then we can use that hypotenuse-like theorem again to see that this piece is also 9.7, which actually gives us one of our theorems. If we have a radius run perpendicular into a chord, it's going to bisect that chord. Therefore, these two pieces are congruent. Now, the Pythagorean theorem could be done on this triangle. X squared plus 9.7 squared equals 12.6 squared, and you'll get the same answer either way, that x is equal to 8.1. Those are the first 3 examples on this worksheet. Here we have example 7. This time I see that this little segment right over here is 4.3. And here the 10.6 is not written in the middle. So 10.6 is actually describing this distance right over here instead. If this is 10.6, then based on what we just talked about, this is also 10.6. If this is 10.6 and this is 4.3, how can we figure out the length of x, which happens to be the radius? We can use what we just spoke about a moment ago. We can use the Pythagorean theorem. So 10.6 squared plus 4.3 squared is equal to x squared. Now, just to save a little bit of time, I'm just going to go ahead and put that in the calculator. 10.6 squared plus 4.3 squared. Now I want to go ahead and take the square root of that answer. I'm going to hit Shift-Enter for a decimal, and we're going to round to just one decimal place here because that's what the instructions asked us to do on the first page. We're going to have 11.4 as my x value. Obviously, it's an approximation because we rounded. And that's it. Number 9. This time we have the radius of 10.4. That's connecting the center to the circumference. And if that piece is 10.4, then so is this piece right here. Now I have this perpendicular segment. That means it must be bisecting this segment. However, I could simply do Pythagorean theorem to find the length of x for this example. So we'll have x squared plus 8.4 squared equals 10.4 squared. That means I'll have 10.4 squared minus 8.4 squared, and then I'll take the square root of the answer, shift, enter. We're still rounding out to just the tenths place, so I'll have 6.1. X equals 6.1. If for some reason I needed to find the length of this piece right here, I would do 10.4 minus 6.1 to get that piece out here, since that's also the radius. All right, number 11. This piece right here, we have a radius of 16.7, and that's also a radius of 16.7. Now, not even sure where we have to go with all this, but I also see that I might need this one. That's a radius of 16.7, as is this piece right over here. I like those because they draw in some right triangles for me and make it a little bit useful for me to potentially find more information. So if this over here is 16.7, and that right there is 15, I can do Pythagorean Theorem to find this, and then I'll find that, which is exactly what I sort of foreshadowed right over there. So I'm going to start by finding this piece, which I will call y. 15 squared plus, this is the y squared, 16.7 squared minus 15 squared. Watch how you're typing this, it really does matter. Then I'm going to take the square root of that. So square root of my answer, shift, enter. I get about 7.3 for the y value. Now, what does that tell me about x? X plus y is 16.7. Since y is 7.3, subtract 7.3 from both sides. 16 minus 7 is 9. 16.7 minus 7 is 9.7. Minus 0.3 is 9.4. X equals 9.4. Again, all of these, I guess, we should really be telling approximately. Here we have 13, and then you'll have to work on numbers 2 through 14 even alongside the odds we just did. So 30 is written over here. That means that my radius is 15. R is 15. If R is 15 right there, well, it's also 15 right over here. Every radius is the same. And this is also 15. Since that's 14.1, then this is 14.1. I'm going to go ahead and find this piece over here, similar to the previous example. It's just set up differently. So I'm going to find this piece first and subtract from 15, similar to before. 14.1 squared plus y squared equals 15 squared. 15 squared minus 14.1 squared, square root of the answer, shift equals, so the y value is about 5.1. Then, since x plus y is equal to 15, that means that x is approximately 9.9. And that's the end of the odd examples on this worksheet. I hope that you are able to find lots of success working on the evens, and I hope this is helpful on having you practice examples involving arcs and chords. Good luck!